a series of work with Charles-Alban Deledalle, Joseph Salmon, and Samuel Vaiter. So it's closely related to Guy talk. So it's about what we call the refitting. So I will start by introduce the problem and then describe our algorithm to realize the refitting. And then I will come to some practical consideration, how you can refit in practice. So what I consider here is for piecewise constant signals. So you have here. Imagine that you have a noisy observation of this kind of signals with an additive Gaussian noise. And when you apply TV, as the guy showed, you have this kind of results. So you can expect to recover the jump of the original solution, but you have a bias, this contrast lost. And so the objective of our work is how to reduce this bias and recover the original signal. So yes, so as I say, it's bias in the sense that if you take different random realization of the noise and you take the mean of your estimator, you won't recover the original signal. And so a natural solution for this kind of regularization is to compute your refitting as a mean value of your observation onto the support of the solution. But the trouble is how to do it automatically. So in practice, which kind of bias can we expect to reduce? So if you have here this noise-free image, the noisy data, this will be Anisotropic TV, and this is the error you have here, which is computed. So you have some lost structures because you have regularized too much, but you have some attenuated structure here, and this is the ones you can expect to recover with refitting. So this is the kind of result we can have when we recover the loss of contrast. So our objective is to generalize this kind of approaches to more general estimators than Anisotropic TV. So first I will consider a general setting where my estimator is a solution of a minimization problem, so a classical formulation for inverse problem where I have a data fidelity term, a convex, F, a prior model of the regularity of the solution with G, and a regularization parameter, and then I can add some linear operator for if there is blur in the observation, if there is a mask for in-painting, and so on. So there are a lot of related works doing this, known as boosting approaches or Bregman iteration, where what you can do, once you have first realized your TV regularization and obtain the red, I don't know if it's red for you, but this red piecewise solution, then you can compute the residual and then apply again your model on this residual and do it iteratively. And so you have an iterative process, and then you have the first solution, you denoise this one, and you add it. But there are several limitations. So first of all, you don't preserve the support of your solution because you have no assurance that when you will denoise this solution, the piecewise constant, the pieces you will recover will have the same jump as your original bias solution. You don't know how many iterations you have to do, and in practice you have to consider some varying parameters in order to have good results. So our objective in our work was to try to generalize refitting for a lot of models, and we want to keep the structure and regularity present in the original bias solution. We want to correct the model bias due to the regularity prior G, and we don't want to introduce any other parameters. And then, if possible, we would like also to handle possibly any black box algorithm where your solution is not the minimum of a given problem, but it's just something that is given by an existing black box algorithm. So you can imagine non-local means or BM3D, or even you take a trained deep network and you want to if possible, correct if there is some bias. One important thing to underline is that with respect to the bias-variance trade-off, refitting is not always favorable in terms of reduction of the mean square error, and so in practice, we have no guarantee that we will reduce or increase the PSNR, but we have other good behaviors of our solution. So I will come now to the first work on this subject. So in order to understand refitting, I will just formalize refitting for anisotropic TV. So I come back to a linear inverse problem where I observe some data, some signal y through a linear operator, more an additive noise. So this is my estimator, my TV estimator for recovering the underlying signal x0. And what is refitting? It's just a constraint least square operation where you want to find, you just want to project your data onto a model subspace, and this model subspace for TV is just the set of signals that shares the same co-support as your bias solution. So if here you have find a jump for this solution, you want that your refitted solution has the same jump, have a jump at the same location. And when it's constant, you want your refitted solution to be constant. But this is only formulated in terms of jumps, and if we want to generalize this approach, we have to understand what is really captured by this model subspace. And so this very simple idea is to consider that this model subspace, it just captures the linear invariances of your estimator with respect to small perturbation. So in order to give you some illustration, so for anisotropic TV, I have a piecewise affine mapping from my data to my estimator. So here it will be my data, and when I apply TV, I have this kind of solution. If I just perturb a little bit my data here, sorry. So I still have here a small jump, and here I stay in the same piecewise decomposition. But if I do a larger perturbation, then maybe this jump will disappear, and then my solution will come to another place here of the possible TV solution. And so the basic idea is to consider the Jacobian of the estimator, and then to define the model subspace as the tangent space of the mapping at point y. And once you have defined this, you can just consider your refitting as the orthogonal projection of your data onto this model subspace. And so this is very general, and you can, here it's illustrated for anisotropic TV, but you can do it for a lot of other models than TV. So in practice, how can we compute this projection? So as I said, for TV, it is well known that the anisotropic TV, the solution are piecewise constant. So what you need to do is to detect the support, but in practice, you have some numerical accuracy issues because you will estimate your solution with a sequence of through a converging sequence that I call here xk. And even if xk is converging to the true solution, in terms of support, it's not so clear because you can be as close as you want as a true solution. You can have a non-vanishing gradient, and if you use this kind of criteria to detect the support, maybe you will overestimate the support, and when you project back your blurry data, you will re-inject a lot of noise. So, which means that posterior refitting is not a good idea. Instead, what we have considered is related to the work of Samuel Vaiter during his PhD, is that for this kind of L1 analysis minimization problem, you have that the invariant refitting that I just introduced in the last slide correspond to the application of the Jacobian to the data. So this means that you can, in fact, using chain rules, you can compute, if you have an algorithm that gives you the solution, the bias solution, you can just differentiate your algorithm in the direction of the data, and it will approximate the invariance refitting, which means the application of the Jacobian matrix to the, in this case, to the data. The first question is, does this derivative sequence converge to the invariant refitting? And for this kind of problems, the answer is yes for most of standard algorithm. So in practice, it's quite simple to see. So here it's the primal dual implementation to compute the bias solution of anisotropic TV. So here you have a nonlinear step and here a linear one. And if you want to compute the invariant refitting, you just have to differentiate each step. So here it's a linearization of the projection, and here it's linear, so the linearization is the same. And in fact, given a small parameter beta here, so which corresponds to deal with extended support, but I won't enter into details, you can show that this sequence, at some point, this criteria will be stabilized, and you will have convergence of your tilde sequence, and that will converge to the invariant refitting. And in practice, it means that you can do both at the same time. In the same time that you are computing your bias solution, you can compute the refitting, and it just doubles the cost of each iteration. So it's quite easy to implement. In practice, if I take these toy images, noisy, for this bias solution, that exactly correspond to the support of the original signal, I can gain the loss of contrast, I had. An interesting thing is to look at the bias-variance trade-off. So I will just here explain this figure. So here, this dash curve corresponds to anisotropic TV regularization for different parameter lambda. So here, on blue is the best parameter in terms of root mean square error, so which is here. And you have this kind of recovery. If you look at the corresponding refitting, here you see that you have a lot of small areas. So when you refit, you inject a lot of noise. And here in red, it's the best refitting we can expect. It corresponds to a higher regularization parameter, where here, so it corresponds to this anisotropic TV solution here, which is over smooth, but it has detected a lot of I would say most of the good support of the original signal, and when we project it back, we have almost no oscillation here. So in terms of root mean square error, it's better to have this one, but in terms of visual quality, it may be, for instance, here with the SSIM, it can be better here because you don't have this small artifact that appear. And if I consider my toy example here, which exactly correspond to anisotropic TV priors, because there are only a square which are eigenvalues of anisotropic TV, then if I regularize a lot, what I can expect is to recover the good jumps of the original signal, and when I refit, I can expect to almost recover the original image. And so this is closely related to what Guy presented, because here this regularization parameter, it corresponds to the time you will have with a gradient flow of TV. And so when you regularize a lot this image, you will get to this one. It removes the high frequencies, and then you can integrate back. And so it's exactly correspond to the back integration you are doing with this refitting. And an interesting thing is that you see that the range of parameters that give you good errors is larger than for the anisotropic TV. So if you directly use anisotropic TV, you have to be careful when you tune your parameter, because otherwise the error explodes. Here you have a larger range, and it was the same here, where you see you have a flat region of parameters, so you are less sensible. We can do it also for anisotropic total generalized variation, where the solution is piecewise affine. So you see here, for instance, in the chimney, your anisotropic generalized TV regularization, it underestimates the height of the chimneys, and with refitting, we recover a better range of values. Now I come to the problems. When I consider now isotropic TV, the model subspace of isotropic TV is the same as the anisotropic one. Is a signal that shares a gradient with the bias solution. And in fact, it's not good at all, because when you have isotropic TV, you have some regions where you have continuous evolution of your solution, and when you refit, so here you have support everywhere, and when you refit, you just inject back all this noise, and this is not good at all. So in this is so a limitation, because we just use the model subspace, that captures the linear invariances, but we can do better by using the Jacobian matrix. So this Jacobian matrix, it encodes some desirable covariant properties, so the relationship between your outputs, the entries of your output with respect to the entry of the data. And this is more interesting to generalize refitting to any kind of algorithm. So I now come to this covariant least square refitting approach. So I again consider a general inverse problem with convex functions. Here I recall that this is invariant refitting, which is the orthogonal projection of my data onto the model subspace. And now I will define a set of refitting operators that should have some desirable properties. So first I want them to be in this model subspace. So for isotropic TV, I still want that my solution has the same constant part. I want it to be an affine map. This is for computational reason, to have some simple things we can compute. And then what we want more is to have a preservation of the covariant, meaning that the Jacobian matrix of your refitting operator should be proportional to the Jacobian matrix of the original bias solution. And then I want some coherence, meaning that if I observe through phi my solution, I want to recover it with refitting. And so once I have defined this set of possible solutions, the covariant refitting is just the orthogonal projection onto this set. And what is interesting is that with all these properties, we have, combining all these properties here, we have an explicit formulation of the covariant refitting, which can be expressed as a linear combination between your bias solution times this rho, which is a degree of freedom. Here I want it to be proportional. This gives me some freedom for the refitting. So times this parameter times the Jacobian matrix applied to the residual here. And in fact, as we are doing some least square refitting, we have an explicit formulation for this global parameter rho. So we have also interesting properties of if phi of j is an orthogonal projector, then rho is 1, and we exactly recover the invariant refitting. So this is the case for anisotropic TV, for instance. And also, if f is convex and g is absolutely one homogeneous, then we have a nice property that the Jacobian applied to the bias solution will give you the bias solution. And then your covariant refitting can be just obtained as a linear combination of your bias solution here and the Jacobian matrix applied to your data, which is here. And then as we have an explicit formulation of the rho, if we can compute these two guys, then we have automatically the covariant refitting, and it can lead in practice to more faster algorithms. In terms of bias reduction, so in fact we have some result I skipped, but for L1 analysis minimization problem, we have some kind of weak bias reduction. So it corresponds here to have a phi j, which is an orthogonal projection, and rho is 1. And when rho satisfies some technical solution, we know that we will reduce the bias, meaning that if you take here some random realization and the refitting expectation, the refitting here, the distance here will be better than the mean distance with respect to the original bias solution. And when it's an orthogonal projection, okay, it's almost obvious because you are doing the projection, so you reduce the bias. So when I come back to my example of isotropic TV, so this was the invariant refitting where we were re-injecting the noise. And now with the covariant one, we keep the structure of the solution, but we gain this loss of contrast we had. Then for people familiar with Bregman iteration, a natural question is why not iterating such a process? So I will just explain what it does. So if we consider still the bias solution, if we do some Bregman iteration, we will iteratively approach the original data. So at convergence, if you apply a Bregman iteration, you will recover your data. And in our case, if we do some covariant iteration, as we must remain in the same model subspace, we will approach the invariant refitting. So meaning that we will, as for Bregman iteration, we just reintroduce noise. And so for us, it was OK just to do one iteration, and it seems natural. So I will now come to some practical consideration. So how to compute this covariant refitting in general. So as I explained, that we have an explicit expression of the covariant refitting. And the main problem is how to compute the application of the Jacobian matrix to the residual here delta. So we can rely on algorithmic differentiation, as I showed for Anisotropic TV before. We can either do some finite difference-based differentiation. So if your restoration is given by a black box algorithm, then you compute your solution. And then you take a small epsilon, you perturb your input data, you apply your denoising algorithm, and then you have this approximation of the Jacobian applied to your data. And then you just need to apply twice your algorithm. So in practice, we have two kinds of methods. First, two-step methods, where you apply your algorithm, then you compute your residual, you apply your Jacobian to the residual using either algorithmic or finite-based differentiation. Or in the specific case of absolutely one homogeneous regularizers, then the refitting, it simplifies as a linear combination of the bias solution and the Jacobian matrix applied to the data. And then if you have your algorithm, you can compute both at the same time with a differentiated algorithm, and it gives you a joint estimation. So as I come back to my implementation of Anisotropic TV, so here it's a one homogeneous regularizer. It's also an orthogonal projection, so rho is 1, and okay, my sequence is converging onto the covariant and the invariant refitting, which are here the same. If I now consider isotropic TV, then it's also a one homogeneous regularizer. So my differentiated sequence will converge here to this tilde x, and then my covariant refitting will be the linear combination. But here, I just have to run one time my algorithm, and it just doubles the cost of each iteration. Just an illustration to see that in painting with isotropic TV, this is the kind of things we can recover. So as before, the structure here that are lost with the bias solution, you cannot expect recovering them, but some of them that were detected, but with a loss of contrast, then we recover a better images. So with Fabien Pierre that presented yesterday, we have also extended this to some color and denoising of chrominance channels. So it's also a one-step algorithm. The only difference here is that the rho is not global, it's a local one. So you have a rho parameter that varies locally with respect to some constraint of possible colors respective to one luminance. But if you have here this noise-free image, this is a noisy one. This is a standard denoised image with a coupled total variation that Fabien introduced yesterday. And this is a kind of refitting we can have. So it's, I hope we can see it, but it's it's more shiny. And so we recover the original colors that are closer to the original image. Then now I consider other kind of denoising algorithms. So for instance, non-local mean, which this model is without any absolutely one homogeneous regularizer. So here, if you have your NL-means code, you just have to differentiate it, and then you apply your algorithm, you run your differentiated algorithm in the direction of the residual, and okay, it's done. So this is some experiments related to this. So here, for this kind of NL-means results, this is what we can recover. So again, you have some attenuated structures here, and you have some structures that were lost and are still lost in your solution. As before, we can look at the bias-variance trade-off, and here it's quite interesting also to see what happens. So this is the best result we could achieve in terms of root mean square error with NL-means. So with here, the filtering parameter of NL-means is increasing. So in terms of mean square error, you have very good result, but I think you can see there are a lot of oscillation, and when we compute the corresponding refitting here, all these oscillations are amplified. On the other hand, the best refitting we can have correspond to this NL-mean result, which is over-smoothed, but it contains the good structures that we can refit after. And so in terms of mean square error, it's better to have this one, but for SSIM result, we see that okay, it's equivalent or even better to have the refitting. And again, you see here that the range of parameters is quite stable, so you can just overfit your solution and then refit, and it gives you good results. And if we now take another image of the fingerprint, which correspond to the prior of non-local means, because here you have a lot of similar patches. So this kind of images better fit the NL-means prior. So here, in this case, we can even recover some solutions that are better in terms of root mean square error with the refitting. Yes, and it's also quite stable in terms of the tuning of the parameter. And now I will show you some example for black box algorithm. So here, what I consider is a finite difference approach. So it is important to underline that here I should have some differentiable algorithm, meaning that I cannot handle any algorithms that start with some quantization. So if you start by quantifying your data, it won't work. But okay, it's a reasonable assumption for variational methods to have an algorithm that is continuous. So that is the reason why, for instance, for BM3D, we consider the implementation of Lebrun, because BM3D just started by a rounding of your data, and then you cannot compute some small perturbations. So we have the same kind of analysis there. So this is the best result for BM3D. But if we look at the corresponding refitting, there are a lot of small oscillation. Whereas if you over-smooth your image with BM3D, you can recover some good refitting. And okay, we did it also for other regularizer like DDID. And this is the same kind of result here. You have a lot of oscillation, small oscillation, and we can have better visual results. So lastly, we have also started to look at what can we do with residual networks. So the trouble here is that we just consider some train network as a black box, so we don't have any parameters that we can play with to see what it will do. But still, it's interesting, I think. So here I consider this residual network that is designed to learn noise to remove. So if I take here this noise level from this, I add noise to this image. This is the result you can have, and this is a clear the clear solution, so it does not change a lot. If I increase the noise level, this is the kind of result I have with this network and the refitting. And if I give a very, very high noise, then this is the result I have, and the refitting is completely awful. But okay, this is like natural because this is a residual that is designed to learn noise. So there is no structure to learn from the noise, so we cannot expect to recover anything. But now, if I look at another version of the same author of networks that now learn how to denoise an image and does not learn the noise, then we have different behavior. So here it's the same. This is my original image. This is my blurred image, and this is what is recovered with this FFD net. So it's quite amazing. This is a clear network. This is a clear refitting. So as before, we have seen with BM3D or this kind of result, we just increase the small perturbations that were not visible at the beginning. If we increase the noise, it's even worse here with the refitting. But the fact is that this network has been learned with data for variance between 0 and 75. And if we now consider very high noise level, so this is a kind of result you have with the same network. And this is now what we obtain with the clear, exactly with the same parameters. So here it's quite interesting because we are able to recover a lot of small structure here that had completely disappeared with the original solution, and still, by just looking at this small variation, we can recover more details. So now this is things that we are looking at because maybe there is still to understand in the structure of the solution of your network. And, I don't know how many time I have. Oui, qu'on reste combien? 10 minutes. Okay, so good. So I have been fast enough, so I will speak about new stuff also. So just to summarize what I've presented. So the covariant least square refitting, it can correct part of the bias of a lot of, not any, but a lot of restoration models. We have no additional parameter, and we have also stability for a larger range of parameter. And in terms of computational cost, it just doubles, so it's okay. It's important to consider differentiable estimator, so without quantization, and to have some regularization prior adapted to your data. And okay, I'm working also on other problems where it's very important to respect the range of the values. For instance, in oceanography, where you want to measure the height of the waves, and you don't want to have this bias. And so this kind of refitting method are very interesting. Okay, there are other works where, okay, this is a lot of related works. So as I have time, I will just talk about other things we are working on. In the specific case of L12 regularizations of which will correspond to isotropic TV, there are other works from the group of Martin Berger that guy mentioned also that consider a different kind of refitting. So what they introduced is the conservation of the sign, because when you refit your solution for TV, you can have a sign inversion. You still have a gradient, a preservation of the gradient, but maybe when you refit, you will change the sign. And so they have considered, this is just a reformulation of their approach. Okay, so this is our model subspace. This is my bias solution. This is the covariant refitting and the invariant one. And what they have considered in this paper is to add some more other kind of priors. For instance, orientation preservation, when you want that your refitted solution has exactly the same direction, the same orientation of gradient. So it will correspond to project your data then on this subspace. They also have considered some direction preservation. So here, this deal with this sign trouble, where the gradient of your solution should be proportional with a positive factor. And then the refitting just corresponds also to the orthogonal projection here. And then we have, like, we can see all this method in the same framework. Here, just to show you the influence of the sign. So this will be Anisotropic TV. This will be our refitting. And this will be with the direction constraint. So here you see that if we don't have the sign preservation, so here we see we have a continuous decrease of the value here. If we don't constrain the sign, so here we can have a change of contrast inversion after refitting. Whereas if we force the refitted solution to keep the same direction as the anisotropic TV solution, then we don't have this change here of contrast. And so this gives us some intuition to define more general refitting methods. In fact, okay, this is a covariant. This is our covariant refitting, and our covariant refitting, so it corresponds to some kind of apply. It's linked to the application, as I say, of the Jacobian matrix to this data, and this corresponds to solve this kind of problem. In fact, where here you just penalize quadratically the orthogonal direction of your refitted solution with respect to the bias one. And so the idea then is to make some compromise between instead of looking just at orthogonal projection of the data onto some subspaces, we can just solve some problems onto this model subspace set. And then we can define very general problems of refitting problems where we consider some penalization function, including either the preservation of direction, of the preservation of orientation for isotropic TV. And this also generalizes, in some sense, the Bregman iteration. And just a few examples to show you. So if I apply isotropic TV to this image, this is the kind of result I will have. With Bregman iteration, I can expect this kind of result. So here, I don't preserve the support of the solution at some point. If I only preserve the orientation, then I can have a lot of contrast inversion with the refitting. If I impose to have a direction coherent to this bias solution, that is better. This is the previous covariant models, and this is the kind of new models we can have. And okay, another example. So this is a quite interesting way to refit a solution for isotropic TV. Okay, so thank you for your attention.
Okay, so we have time for questions. Who's first? Yes?
Okay, so thanks a lot for your talk. I think you really proved a very important theorems, the one you mentioned about the convergence of differentiation algorithm. I'm wondering for which function do you prove it? So for instance, is it also proved for L1, L2?
No, for L1, L2, in fact, no. We don't have, in fact, sorry. Yeah. In fact, for what happens is that for L1, here you just have a stabilization of the sign. And so you can show that when you are close enough, then this criteria won't change and okay, it will converge. But here, the direction, okay, you can have a change of direction asymptotically. So you have, as your direction can change, then this operator, you can be as close as you want of this asymptotic dual solution, but this operator may change. So it means that you change the problem you are solving. So in fact, here we don't have any guarantee of convergence. In practice, it's completely okay, but we know that we could design some counterexample, I think, for
you think the theorem is not true for L1 and L2?
I think for, yes, the theorem I wrote is just for L1. I didn't write it for L1 and 2. Okay, asymptotically, yes, it will converge, but we won't have, I think, convergence infinite time. Yeah.
Okay, thank you.
Okay, thank you. Another question? No? Okay, well, so thank you, Nicolas.
Thank you.